So in this video, I would like to wrap up our discussion of solving systems of equations using linear algebra methods by talking about how to go through the entire system solving process, start to finish, completely using linear algebra techniques, using linear algebra to perform the elimination, and using linear algebra to perform the back substitution and looking at the augmented matrix and interpreting the results of that augmented matrix. So if you are solving the entire system completely using linear algebra methods, if you're solving systems of equations using Gauss-Jordan elimination as opposed to just Gaussian elimination, the overall process is this three-step algorithm. So you take your system of equations and you start by writing it as an augmented matrix. Then you take that augmented matrix and you perform Gauss-Jordan elimination as we talked about in the previous video. Once you have done that, you take your matrix, which is in reduced row echelon form, and you write it back in terms of the original variables to get the solution to that system, or potentially to realize that there are infinitely many solutions, or potentially to realize that there are no solutions. So to demonstrate the full process of solving a system of equations using linear algebra techniques, let's go ahead and solve this system of equations. And step number one, steal the coefficients and the values in the system and put them into an augmented matrix. So that we have 3, 4, minus 2, bar 0. 2 minus 3, 4, 11. 1 minus 2, 3, 7. Now, as usual, we're going to start this process by performing Gaussian forward elimination on this matrix and start by writing it in row echelon form. Now, we actually have already done the forward Gaussian elimination on this augmented matrix in a previous video. We did the forward elimination back 2 videos ago on this system and on this augmented matrix. So let me go ahead and just save a little bit of time by recycling some of our old work. So at this point, all that I need to do to perform the Gauss-Jordan elimination and get this into reduced row echelon form is I need to turn all of the pivots into ones, and I need to eliminate all of these values above the ones in their respective columns. So all of the pivots are equal to 1 already, except for this guy here in the bottom right. I would like to rescale row number 3 so that that pivot of 9 is turned into 1 instead. So I'm going to go in and scale row number 3 by a factor of 1 over 9 to turn this 9 into a 1. Both of those divided become 1. Okay. So having now done that, I want to go ahead and attack these entries above the ones in the matrix. So if I would like to cancel out the -2 here in the second row, I'll need to scale by +2 to eliminate the -2 in this position. So if I do that, again, because of all the zeros that are currently on the left-hand side of this matrix, the only entries that'll actually be affected by this action are the 2 entries on the far right side of the matrix, the one in the Z's column and the one in the outputs column. So the Z's column will cancel out by design, and I'll get a 0 in that position. And so let's see what happens to what is going on in the outputs column. So if I take this 1 and I multiply it by +2 and I add it to -3, we get a result of -1 there. Let's also go ahead and cancel out that value of 3 above the 1 in the third column. To cancel out that 3, I will attack it using a -3. By design, I will get a 0 in the third column. And so let's figure out what's happening in the outputs column. And so negative 3 times 1 plus 7 is going to give me a 4 in the outputs column at this stage. Finally, let's go ahead and clear out this entry minus 2 above the pivot in the second column. So to get rid of this minus 2, I will attack it using a positive 2. We get this minus 1 in row 2 times this scalar of 2. So negative 2 plus 4, result 2. Okay, so now our augmented matrix is in reduced row echelon form. So the Gauss-Jordan elimination process has been completed. So now all we need to do is interpret the results that we are given here. Remembering that the first column stores x's, the second column stores y's, the third column stores z's, and then this final column stores the outputs of the system. So if I now interpret this reduced augmented matrix, what I'm getting is x equals 2. That is how I read the first row. I'm getting y equals minus 1. That's how I'm reading the second row. And I'm getting z equals 1. That's how I'm reading the third row. So this system has one unique solution consisting of this point. And to confirm, this is exactly the same answer that we got 2 videos ago when we were just using Gaussian elimination and then doing the back substitution. And that's as it should be, right? Like the Gaussian elimination method, the Gauss-Jordan elimination method, and the old school like algebra method. All of these are just different ways to achieve the same results. So no matter which method we use, if we execute the method correctly, we should be getting exactly the same solution set in any case. So just for a more authentic example of this process in action, I was on YouTube the other day and I'm watching a video series from a sophomore level electrical engineering circuits class. The instructor of the circuits class is in the process of trying to analyze and understand a relatively complicated electrical circuit as described in this diagram. So he uses a combination of Kirchhoff's current law and Kirchhoff's voltage law in this circuit, and by applying those laws to this circuit, he arrives upon a set of several different equations that are relating all the different voltages and currents in the circuit that you're seeing in this diagram. And so his system of equations for this circuit relating all these voltages and currents, he's written the actual system of equations over here on the left. But you can see on the right-hand side, he's taken that system of equations and he's expressed it now in matrix format. So the matrix form that he's written down, here he's got the coefficient matrix for the system that he's working on, what we have called in this class capital A. This vector here is storing his variables, which we have called in this class the vector x. And on the far side of the equation is his outputs vector, which we have called in this class b. So let's go ahead and use Gauss-Jordan elimination to solve this system from this circuits class to figure out these 4 unknown voltages and to figure out this unknown current for this particular circuits problem. This is by no means something that I would be doing by hand. To do Gauss-Jordan elimination by hand on a system that has 5 equations and 5 variables would take a terribly, terribly long time to execute. So I'm going to go ahead and I'm going to do this by computer, and I'm going to do it by computer just on whatever I have access to. Like right now I can most easily access Wolfram Alpha, so let me go ahead and approach this on Wolfram Alpha. So on Wolfram Alpha, I'm going to type in the augmented matrix corresponding to the system that's being represented here in matrix form. And then I'm going to ask Wolfram Alpha to row reduce that matrix. And then I'm going to interpret the results of that row reduced matrix. So let me go ahead and type in the augmented matrix corresponding to this system into Wolfram Alpha. Okay, so I have typed the augmented matrix corresponding to this problem into Wolfram Alpha. If you've not typed matrices into Wolfram Alpha before, those are written using curly brackets, where you have curly brackets surrounding the entire matrix, and then you have another set of curly brackets surrounding each row of the matrix. So you can see this first row of the augmented matrix consists of 9, -4, 0, -2, 0, and then the output 384. So I've surrounded that list of values in a curly bracket to form the first row, and so on and so forth. And then I just asked Wolfram Alpha to row reduce that matrix. And the result that it's giving me is right here. This is an exact form, so let's go ahead and approximate it to get these values as decimals. So if I've typed everything in correctly, let me now go ahead and interpret this result in the language and in the notation of the circuits problem that Professor Ammerman is working on here. So let's notice that the order of the variables in Professor Ammerman's matrix form are V1, V2, V3, V4, and I sub x. So if we think about linking up the entries in each row of the matrix with the entries in that column vector, we can see that this first column of our augmented matrix corresponds to the first variable, V1, the first voltage. The second column corresponds to V2, the second voltage, then V3, the third voltage, V4, the fourth voltage, and finally the unknown current I sub x. So bearing that in mind, if we then interpret the results that Wolfram Alpha is giving us, the first row of the reduced matrix says that the voltage V1 would be equal to approximately 108.8 volt. V2, the second voltage, would be equal to 137.8 volt. V3, the third voltage, would be equal to -5.9 volt. So it looks like a voltage drop is happening there. We have V4 being equal to 22.3 volt. And then we have the current IX as labeled in his circuit being equal to 4.8 amp. So this would be the solution to the system of equations that has been obtained by applying Kirchhoff's current law and Kirchhoff's voltage law to this particular circuit. And so this is a very common application of systems of equations as solved using linear algebra techniques in a STEM class such as electrical engineering circuits. In today's video, we talked about the full process of solving a system of equations using Gauss-Jordan elimination. If you have a system of equations, especially a system of equations that's relatively large, the typical process is to take that system and write down the augmented matrix that represents that system, and then perform Gauss-Jordan elimination on that augmented matrix to completely rewrite the entire object in reduced row echelon form. If you then remember what each of the columns of your augmented matrix stands for, you can then interpret the results of that augmented matrix to understand the solution set to your system.